Okay, so let's get started. Hi everyone, welcome to lecture 3. Today we'll talk about linear classifiers. So before we get into the content, so just so you know, today is the due for project 0. And I sent out a Google form for you to submit as zip files. Good news is we have AutoGrader set up. We just need to provide credentials. So for project 1, I think it'd be nice to have AutoGrader so you can submit, figure out issues, and keep working iteratively. I think that would be nice to have. Okay, so it's due tonight. I've already seen a few submissions, so which is great. I hope it will roll out in the evening. Okay, moving on to project 1. So this will be released by the end of today on the website. And this will be on k-nearest neighbors and linear classifiers. So in terms of where we are in the course, the second week, not too far along in the course. So today, project 0 is due and project 1 is going to be out. Okay. So quizzes start from next lecture, which is on Thursday. So the way it will happen is the quiz will be open from 7 a.m. in the morning on the day of the lecture. And it will close before the class, just before the class, around 2:30. And it's going to be like a very simple question. You should hardly take a few minutes. It will be either yes or no, like true or false, or you'll have multiple options and you select one. And it shouldn't take more than 5 minutes. And once you open the quiz, you will have 15 minutes to finish it. And so it basically covers the materials from previous lectures, maybe a couple of lectures before the quiz, and also your graded projects so far. So you can compare, for instance, if you're far along, if we are far along in the course, we could probably talk about k-nearest neighbors too. So we can compare what's happening at that point versus what happened earlier in the course. Okay, so a little bit of recap. So we saw image classification in the last lecture. It's a core computer vision task. And the goal here is given an input image or a matrix with a bunch of numbers, your classifier should be able to predict one of the labels that was provided. And we saw that we discussed a little bit on semantic gap, because the way we perceive scenes versus the way the algorithms perceive the scenes. We talked about viewpoint variations, illumination changes, and intra-class variations, how these things actually make the image classification a challenging problem. And we touched upon the aspect of data-driven approach, which is basically the core of this class. And especially for classifiers, we talked about 2 different blocks of code. One is going to be a function that does training, the other one that does the prediction. And here is the training set that you'll be using for this course, which is props, the data set from Michigan. Okay, jumping on to linear classifiers. Just like how we saw image classification to be a building block for doing object detection, pose estimation, and in general, robot perception, linear classifiers are a good way to think about training neural networks. So this will be a building block for neural networks. And we will talk about the mathematical foundations behind linear classifiers. So it prepares you for more complex algorithms that you will look into in this course in the next few lectures. And we saw this data set, like I gave a snapshot of this data set in the last lecture too. This is similar to CIFAR10, which has 10 classes. Each of the images in this data set will be 32 × 32 RGB images. You'll have 50K training images and 10K testing images. I will be posting a link to a video, which is actually a discussion section that happened at Michigan, where the staff actually talks about the data set, what it contains, and how to access them and play around and look at a few images from the data set. And this is what you'll use from project 1 till project 4. Okay, so if we take a parametric approach, what we mean by a linear classifier is it's going to be a function that takes in your image, X here in this case, and have a few parameters, let's say W, and it gives out a score for each of the labels that you have in a data set. For instance, for the props, you have 10 labels. It's going to give you scores for each of these labels. This is a simple way of looking at a classifier. Like given an input image and a bunch of parameters, going to spit out the score. Now, we haven't decided what this f is going to be, right? We are talking about linear classifiers. So this function is, you can think of this function to be a linear function, where here it is a simple multiplication between matrices W and a vector X. So to go a little bit into details, your f is going to spit out 10 different numbers. You can think of that as a vector with 10 elements. And matrix here is going to be a 10 cross 3072. 3072 because the image here has 3072 pixels. So we have a vector of 3072 as the number of elements. So simple matrix multiplication. And you can add a bias term because if you want your classifier to be more expressive, you can add a bias term to your classifier. So this is how you would look at in an algebraic standpoint. Now let's take a simple example to kind of think about how you would use this, let's say in your PyTorch implementation. So you should be able to do that in a way because I think P0 is due today. So if you have already played with the PyTorch tensors, you should kind of visualize this in that fashion. So let's say we have an image that is of 2 cross 2 size. You will convert that into a vector. And then you would, let's say we have a random W here, which is 3 cross 4. Again, 3 being the number of labels. 4 is the number of elements that you would get from your input image. You do a multiplication and add the bias term, and you get a bunch of scores for each of these labels. And we are talking about only 3 classes here in this example, like crackers, mug, and sugar. So that's why you have 3 cross 4 as the dimension of W. Here?
These 3 labels are crackers.
Exactly. Now you can imagine if it is for the props data set, and assuming your input image is 2 cross 2, you will be looking at 10 cross 4, right? That's one way to think about the dimensions. So we saw this from an algebraic viewpoint, right? Your multiplication of matrix with a vector and an addition operation. So you can also do a bias trick to avoid the addition operation. You can add one element to your input vector, and you can include the bias term into your matrix. So this way, you don't actually have to do the addition separately. So this saves some computation if you're looking at, with large weighting parameters. Okay, so the other thing to kind of have back of your mind is that you're talking about linear classifiers. So if you ignore the bias term to some extent, if you scale the input, your output also scales, right? So here is a simple example. Even though you're just changing the alpha parameter for this image, you see a different scores. So the semantic gap still exists to some extent, right? And now let us take a different view of this particular operation. So you can also view that as an inner product between your image and 3 different weight matrices, where each of them could be considered as a template corresponding to a particular label. So what we did here is basically took the first row and created an image 2x2, similar to the image that we have from the input. And basically, you're doing the inner product between this matrix and this matrix, and adding this bias to that to give you the score. So we just like modified the W in a different way, but the operations, but the output is the same. Now, while looking at this, we can also try to visualize what's happening for each of these matrix that we see here. For instance, for this particular data, because we have 10 labels, you'll have 10 of these matrices. So they act kind of like a template, and we are trying to see if the input image matches to one of these templates. So these are the images that was created by looking at the row of the entire weight parameters that we have from a linear classifier. So you can actually do this in the project one, and you can visualize what your we call this templates, but you can visualize this in your code once you train your linear classifier. And yeah, like I said, you have one template per category, but there is also a caveat to that because it cannot capture everything about that object. It kind of gets biased to the images that you will see in the data set. So for instance, here, this is the mustard bottle. And predominantly in the data set, it's actually in the upright position. So that's why you see that the template that was created after the training as your weights kind of looks like this particular image. But let's say if you have, it's kind of biased to this particular pose, but you also see a blur on the sides. So it is also seeing other orientations, but it's kind of biased to this particular pose. The other example here is this tomato can soup. You can see that it also kind of remembers the label of that particular object. So you'll be able to see this, and I think this is cool to visualize what's happening with the weights when you train your network on a particular data set. Okay, yes.
So does that WXSD model, does that only apply to grayscale economics?
No, it applies to.
Or more specifically, is that like implemented using grayscale, or where do these values come from?
Okay, so for this example, you mean, yeah, in this example, we are only considering like one channel of the entire observation. But yeah, when you're working with the data set, you'll have 3 channels.
Okay, gotcha.
Yeah. Yes.
Is that the bias, like how does it play a role does that help navigate through that ambiguity of pose and
I don't think we can, but I might be wrong. I can get back. Yeah, yeah.
this is essentially about a template actually.
Right. So I don't think we can actually visualize the bias. I think, but I might be wrong. I can get back to you on that. Yeah, basically because you're adding one value to all the pixels. So I'm not entirely sure how we can visualize that, but I will get back to you on that. It's a good question. Okay, so we saw algebraic viewpoint, and like now, and we also were able to visualize these weights to some extent. Let's take a look at the geometric viewpoint. For instance, let's say we are considering only one pixel of the input image, and that pixel is taken from 15,8 for the first channel, which is the 0 channel, which is the red channel here. And let's say we are looking at the classification scores from a learned linear classifier. So the value of the pixels could be 0 to 255 or 0 to 1, depending on how you normalized your values. You would actually figure out which class it is by just like applying to each of the labels that you have. So you will get a score for each of the labels in your data set. The way to look at it is like, depending on the value of your pixel, it would say, it would get a score for each of the labels. And you can say, by comparing the scores of each of the labels, you can say which label that particular pixel is saying that object is, right? So in this particular scenario, let's say it's more towards the red side or redder side. If you pick these, if you pick that particular value, you will see that it's belonging to the cracker or the pizza box in this case. Now, this was easy when we are looking at one particular pixel. Now, if you start growing your dimensions, let's say you are looking at 2 pixels. So the x-axis and y-axis are actually pixel values, and your scores are coming out of the board. Like it's actually a plane, and it's cutting at that particular location when you're when the scores are 0. But so this is how it would look like if you're looking at 2 pixels. Now you can also try to think about what happens if you are moving in a particular direction from the hyperplane. For instance, when you're moving this way, you are trying to match it closer to the mug template, right? If you're looking at the other 2 classes, it happens the same way. When you're moving in that direction, you are matching closer to that particular template. Now, this is already hard to visualize to some extent, right? We are like, we're talking about 2 pixels. So this would look something like this. There are hyperplanes cutting each other. And we are talking about linear classifiers. So these are planes and not surfaces yet. Now you can imagine, like, if you move from 2 pixels to the entire dimensions of the image, this would be hard to visualize, but still in that high dimensional space, you're talking about hyperplanes cutting each other to do the classification. Yeah, any questions so far?
So
yes.
In this graph, the X and the Y would be the pixels, and then the Z would be
the scores.
The scores.
Yeah.
Okay.
And we are intersecting in that 3-dimensional space. Okay, so some hard cases in the linear classification, like this is probably easier, or you probably need another dimension to think about this, but this is one of the hard cases. Like you have first and third coordinates being part of one class, and the second and fourth being part of the other class. How do you figure out a plane that would like do this classification? The other hard case is like, for instance, let's say you have a ring within which it's class 1 and the other is class 2. So you can come up with different cases. Like, so there are problems in which the linear classification is never going to give you 100% accuracy. Like it has to be completely separable for you to have a linear classifier give you 100% accuracy. So we will move towards that in the later part of the lectures, but the limitation is kind of hard-coded into the linear classification or linear models. So we saw the algebraic viewpoint. We talked about how we can manipulate the matrix multiplication to some extent. And then we were able to say, okay, you can also visualize the weights particular to each of the labels. And we also saw like how this looks like if you're thinking about it from a geometric viewpoint. Now let us talk about like, so we only talked about like scores earlier, right? We said, okay, there is some W that was learned, and we only talked about scores. Now, can we think about like what is a good W? For instance, during the training process, you are like changing your W or the network parameters. So we want to at every point figure out, okay, is this a good W? Am I doing good, or am I like getting worse from the previous iteration? So today we'll talk about loss functions to some extent. In the next lecture, we will talk about optimization routines that would iteratively improve your W parameters during the training. So to do that, in today's lecture, we'll talk about loss functions, which basically measures your the current trained model or the W. The lowest, if the loss is low, we say that we are doing good job in terms of classification. The loss is high or huge, then it's a bad classifier, bad model at this point. There are many names to this, so you can call this objective function or cost function. And I think in reinforcement learning scenarios, we generally think about negative of the loss function, which are often called reward functions, profit functions, utility functions, so forth. So there are different ways to look at this particular function. This entirely depends on your training data. So for instance, let's say we have samples of images and its discrete label. The way to compute a loss for every single sample in this data set or training data is to let your model give an output and then compare that output with the label. So that is a loss. And you would compute an average for the entire data set that would give you the entire loss at that particular instant of training. So let's take an example, and here we'll talk about cross entropy loss. So let's say we have an image or a image of each of these categories, and you have a linear classifier that gives you scores for each of these labels. So for instance, if you give this particular image, the classifier or the model is going to say, okay, for cracker it's 3.2, mug is 5.1, sugar it's minus 1.7. Now let's walk through and see how to calculate the loss. So first of all, we need to think about this in terms of probabilities. So these are raw numbers right now. So the probability here is calculated as exponential of a particular score divided by the sum of the scores. And right now it is unnormalized. We call this logits. We will convert that into probabilities by just doing exponential. So exponential of 3.2, it will be like 24.5. And still these are not normalized. We need to think about probabilities from 0 to 1. So you will sum them up and divide. So you'll get probabilities that are 0 to 1. Right? Now, for the cross entropy loss, the loss is defined as negative log of the probability of that particular score. So here, for this example, it's 0.13. And if you plug into minus log of 0.13, you'll get like 2.04. And if you think about it, we want it to be close to 1. Right? The probability should be close to 1, which means the loss will be close to 0. Because log of 1 is 0, so that's what we want. This is called maximum likelihood estimation. I'm not going to go into the details. So from this, you can probably learn about this in other courses, especially in machine learning courses. Now we are comparing with the correct probabilities, right? Like we have a distribution that says this is what we expect out of the classifier, and this is what we currently have. There is also another interpretation of this. So if you think about information theory, this can also be referred to as KL divergence, and the entropy has a relation to this particular divergence. So I think this will be something, it's an interesting way of looking at it. If you're interested, I would say probe further. But to some extent, you know what we are doing here. So that's the loss that we computed. And we are trying to maximize the probability for every class in the data set. So let's talk about, let's think about a few things here. So what do you think is the minimum and maximum loss that one can expect based off of this formulation? Anybody wants to take a guess, answer? So loss is negative log of the probability. What could be the minimum and what is the minimum and maximum possible loss? I heard something. Minimum zero. Positive infinity. Yeah. So minimum is zero because you would not get a value below zero because the probabilities are ranged from 0 to 1. So 1 will be the maximum value for probability. Plug that in, it will be 0. Whereas maximum value for the loss can be positive infinity. Yeah. So min 0, max positive infinity. So if, let's say, if all the scores are some random values, and this is good, by the way, when you're trying to train a neural network, you want to know what's happening so you can debug your network. So let's say if all the scores are random, small random values, what do you think would be the loss? Why 0.5? Let's say the number of classes that we are talking about here are 10. Let's say we have 10 classes. Negative log of 0.1 because the denominator is the summation of all of them, right? So we are looking at the probability is 0.1, and then if you apply, the loss would be somewhere in 2.3. Is this part clear? Yeah. Okay. So let us talk about a different loss, multi-class SVM loss. It's very interesting that this loss has a margin that it would like to be away from the other scores. I think we'll walk through a few examples to kind of like understand this completely. So if you're looking at the loss function, and this is, let's say, the scores that we get for the correct class, the idea is to always maintain this particular margin. So if you want to look at it mathematically, the loss function is defined as summation over incorrect scores, in which we are trying to see what is the value between 0 and so this particular one here is a margin that we are talking about. So I think it's better to just look at some examples to understand. So let's say we have 3 test images from 3 different classes. And for each of these images, you get a score from the classifier. Now, if you look at the first one, for the first image, let's say these are the values that you get. If you want to plug that into this particular equation, we are looking at only, so we are looking at only the cracker here, right? So we are looking at, in the summation, we are looking at only these 2 values. We are not going to do this because that's the ground truth we are expecting. So you have 2 elements in the summation. In the first one, we are talking about 5.1 that we got, which is SJ, subtracted by the value for your true label, which is 3.2, and adding this particular margin. And the margin need not be 1; it can be any other number. So I'm just like plugging that as an example here. For the second term, we are using for the score that we got from the square, right? So again, 0, minus 1.7 minus the 3.2, the value of the cracker, plus the margin. And if you look at it, what's happening here is that it is trying to use the difference between these 2, right? Among these 2 values, this is the value that is closest to the true value. And it is saying that it is beyond the margin, which is 1. So it constitutes like a bigger number from the loss. Whereas for the term that is part of this sugar, we are not getting any value from the second element, which is just 0, because it's already too far away from the original, like the ground truth value, which is 3.2. So the loss function is entirely dependent on the value of that your classifier is giving out for the true label. Yeah. So you understand this particular loss function? So earlier we talked about cross entropy loss, which used probabilities. Here we are talking about a particular loss function that is using a margin to keep it separate from the other classes. We are talking about multi-class, so there are multiple classes, so it's trying to keep away from the other classes. So let's look at the other one other example. So let's say we are looking at mug. For the true label, the score is 4.9. So the entire loss is being computed with respect to that. So with respect to 1.3, it is away from the margin. The margin is 1, right? So it's quite away from that. So it does not give you any loss from that because it's already doing well. It's away from the true value. The 1.3 is too far away from the true value. The second term, again, it's far away from the true value. So both of this does not give anything to the loss. So the loss is actually 0 for this, meaning the classifier is already performing well for this particular label. Yeah. Okay. Now, if you look at the third one, here the classifier is performing poorly, meaning you should have a higher loss, right? So that's what happens if you plug that. So minus 3.1 is the reference value that we'll use. And let's say we plug that for Cracker. It's like 2.2 minus 3.1 plus 1, and it's 6.3. So you get that contributing to your loss. And the same thing with the other value as well. So this actually has a higher loss as opposed to the other two labels. So the overall loss for this data set, I'm talking about these three images being in your training data, you will get this particular loss. Okay, so let's probe into a few. I'll have more questions on the slides when I upload, like a few more questions, but let's look at a couple of examples here. So what happens to the loss if the scores for the mug, that is this middle column that here, changes a bit? So imagine adding some values to these numbers, small values, let's say less than 0.5. Sorry, nothing will change, right? Yeah, because it's already doing well, and if you're only adding small values, it's not going to contribute to the loss. So what are the minimum and maximum possible value for the loss here? In the earlier case, we saw 0 and infinity, like positive infinity. What happens here? Yeah, it's the same thing, right? 0 to infinity. If all the scores were random, let's imagine that it's all random. And let's say we pick from a Gaussian that is 0 mean and some sigma. So you have like a distribution from where these values are being picked. Can you imagine what the loss would be? Yes.
Would it be the mean of the distribution plus the margin?
Yes. What would be the mean of the distribution? 0, right? So let's say this will be 0 on average. So only the margin is going to contribute. So the loss in this case would be
Number of classes.
Yeah, number of classes minus 1. So that would be the loss. Okay, so let's compare both these losses, cross entropy and SVM loss. So let's look at these three values here. And let's say these are three different classifiers that are giving three different scores for three different labels. And let's look at only the first label, which is in the green color. we're looking at loss for that only for that particular label. Can you think of what is a cross entropy loss here? What is the SVM loss? You can also discuss with each other if you want. Let's take a minute.
Okay, yes. Oh, yeah.
Yeah.
Don't think of computing the exact number. Just try to compare like both these losses between each other. Like, is it zero? Is it non-zero? Is it greater than whatever? Kind of, yeah. Any volunteers? Anybody wants to? Who hasn't answered before? If you guys want to try, let's give somebody else a chance. Any answers? Yeah, I thought you were. No? Come on, it's okay. Yeah, somebody from there. SVM loss is zero. Yes, SVM loss is zero. What happens to the cross entropy loss?
And to calculate it easier, you can just get that exponent SYI down.
Right.
And then all you have to do is just get the difference between.
Yeah, it's basically some value, right?
Yeah.
Whereas SVM loss is zero. That's the difference I'm looking for, right? So it's some value, but not exactly zero. That how. So you want to think about because when we deal with probabilities, there's going to be some residual. So you'll have some number. Whereas SVM loss is kind of different. It's trying to maintain that margin, and there are if and else scenarios that makes it very discrete. And what happens to each loss if you slightly change the scores of the last data point? Yes.
For the SVM loss, it doesn't change except for the second one,
Mm-hmm.
because if it crosses the margin, of course, then you get a positive score.
Right. So because the margin is one, that is something to pay attention to, right? That will have an effect only for the second one. For the others, it will be zero. It'll be the same. For the cross entropy, obviously it will change from whatever we saw earlier. Okay, one more question. What happens to each loss if you double the score of the correct class from 10 to 20? Will something happen? Not for SVM. For the cross entropy, you'll see there's going to be a change, right? Sorry.
expecting a task to get better, which means decreasing.
Yeah, so the loss is decreasing, so which means it's getting better. Yeah. Okay, so to kind of recap, we're almost at the end of today's lecture. We talked about the algebraic viewpoint of the linear classifiers. We saw how we can visualize the weights. And we also saw like the geometric viewpoint of the linear classifiers being hyperplanes in higher dimensional space. And we looked at two different loss functions. This is what you'll use for project one, both these loss functions. And we looked at scores. We looked at how to think about the values that are coming out of these loss functions. And in the next class, we'll talk about how to iteratively improve your models like based off of your loss functions. And it'll be on optimization. Okay, so we have time. If anybody wants to discuss about final projects,